Um, Very cool. Everything's just working and I can go. Okay, this is great. So I guess by way of introduction, again, my name's Gardner. I'm a senior scientific consultant and lead product technologist at BioTeam. So exactly as Terrell said, we have 2 talks, and I was told we were going to have prime slot, which I've now figured out is keeping you from lunch, so sorry. But we're going to do 2 talks. So mine's more of a system architecture type talk, and then John is going to be really talking about a lot of the open source work and other development stack work we've been doing with iRODS. And so hopefully one of those will be probably interesting to you, one of those not so much. If both are, you're my kind of unicorn. So a little bit about BioTeam, just one slide. So we're a high-performance consulting and products company. We have deep expertise in science, and we do a lot of work spanning infrastructure areas, bioinformatics, other informatics, software development. We do a lot of assessments in organizations, so we're in and out of a lot of life science organizations on a yearly basis, and that really gives us a very broad view of the landscape. So we've done this for 15 years, and in a few of those years, starting in 2011 for our BioTeam members, have been working with iRODS. So we have to thank Regan here, because back, I remember for myself in 2011, as a supercomputing conference, we were really, at the time, I was managing a lot of sequencing data across a bunch of core facilities, as well as other instrument data, and going, how do we harmonize all this? How do we lifecycle all this? And there was this very smart, very bright, energetic fellow by the name of Regan who introduced me to iRODS. So through BioTeam, we've done a number of consulting engagements with iRODS. We continue to see more, spanning working with vendors as well as directly with customers and doing custom development work, et cetera. Why we continue to be really interested and fixed on this area is that data management is just a critical mountain. Those of you that may be familiar with BioTeam see us give trends from the trenches or now town hall type discussions about the state of life sciences. And data management is still not a solved problem by any means. It's a critical mountain that must be climbed. We won't ever get tired of talking about it until we feel we've solved it, and really solving it is more of a journey than a destination, as all of us in this room have probably figured out. So we're just actively engaged with the scientific community from many angles to solve this problem. So I want to take a pause real quick for now. I'm getting into the work I'm going to talk about. And just want to thank John Jacque, Alex Umansev, Marcus Dietrich, all from BioTeam, who all chipped in and did work along the way on this system level architecture work I'm about to talk about. In deploying iRODS, we really feel data management and understanding metadata, triggering rules, all these things should happen through the entire process of dealing with research data. So that means even during active processing. So while we think iRODS is pretty cool, a lot of our motivation was around how can we kind of work with it even at a faster high performance level than kind of the typical active archive role it's played in the past. So some of the problems we were thinking through and encountering are, resource servers were really designed around more of a direct attached storage model. They kind of assume exclusivity over the data they manage. Again, this is okay in the active archive model, but when you have distributed parallel storage, say, being managed under iRODS, you kind of lose a lot of the properties that it inherently has. And one of the things is you end up creating multiple copies of the data in order to provide resiliency, which on expensive fast storage is not good. It's basically the problem people run into designing storage systems quite often, where you're effectively building a huge RAID 10 as you add media and systems, and it's just really a non-starter in a lot of those use cases. And so also, when a resource server fails, data is dropping off the grid if there is only a single replica. And if the catalog fails, right, you lose access to everything for the time that it's down. And those are, again, challenging in environments that have different requirements than that. So having multiple copies of the catalog, say we have active multi-master databases and we want to scale those, Sounds good until you start doing it with petabytes upon petabytes of data, and we think that there's a lot of value in putting a lot of metadata in there, right? And a lot of other things in the catalog to make your data system more powerful and help it understand your data better. Doing that is going to, you know, with multiple copies is going to get expensive and difficult very fast. So also we noticed a lot of folks want to move into using iRODS in addition to their existing storage architecture. And they're not necessarily ready to have a huge hardware footprint, add a bunch of servers and, you know, really go for broke to put it in production before they can even really test it. So we've wound up over the years with a lot of people doing POC type stuff. So what we really wanted to be able to do was have iRODS get deployed without additional hardware and give people a good at scale representation of what it can do for them. So, you know, so the question here and the motivation is just saying, you know, could we get the catalog and resources that have the same resiliency and scalability that distributed storage systems have today and have evolved, you know, as iRODS has evolved over the years, what the average center has in terms of storage has evolved. So, you know, how close could we get to that? So the reference architecture we have right here is basically having two storage controllers. Each of them has a set of VMs on them. There is distributed shared storage backing it. So every VM has a mount and is serving out, you know, that distributed storage. Say if it was a distributed parallel clustered storage, these would be like your OSSs or your NSDs. So all of them has a view of all of the data. And in addition to that, what we've added on top is co-residing with, say, these NSDs or OSSs, et cetera. We have the iCAT, the backing database for it, as well as resource servers. And so the reason there's an index after resource server is in the past when folks have done this, sometimes they've kind of tried to collapse and create a single resource backing the parallel distributed cluster and then fake, you know, by giving you a client, you know, a particular NSD or OSS to talk to, they will give them a view of the resource server. But actually in this model, we are uniquely identifying, and essentially you can think of a named resource server as having affinity with a particular VM in this design. So, you know, that's feeding into high-speed local network, which is being accessed by clients. Other thing to note here is that there is actually no load balancer in front of all these by design, so that you get all of network connections coming out of all of these VMs. And so you have all connectivity between the distributed shared storage and the clients. And this may seem, you know, if you're looking at this like, well, of course, so what's novel here? When you deploy iRODS using resource servers and iCAT servers that are outside of this and not converged in with the storage itself, you end up creating an inadvertent bottlenecks where you have to traverse the network interfaces of those systems and you don't get the full potential performance of your backing storage. So the other thing here that's new is, you know, how do you handle failures? So here we're basically seeing, you know, one of the VMs has failed. The distributed storage knows how to take care of that. iRODS really doesn't until these changes I'm about to show you. So we effectively here have migrated over the resource onto another system, and that VM is able to now service both of those resources. So you still maintain access and connectivity to all the data. Same happens when you continue to fail, and you could even fail right, you know, one of the iCATs. And so I stopped here, and bonus points for you can tell me why is if we continue to fail, we would lose quorum in the cluster. But technically, strictly speaking, you can essentially fail down where only a single VM is running as long as it happens to be one that you've put the iCAT on, and you'd still have a full slice. That's what these lines are meant to be, is connectivity between the clients and distributed storage, and you'd still have it at that point. So basically, let's go through the tenets of this talk and how they relate to this. So we see the solution is converged because it's deployed on the storage controllers. We're not adding additional hardware or server instances. Less to manage is good. We think iRODS is actually important enough that we want it to co-reside and really be kind of a feature, almost like people expect NFS or SMB. Well, iRODS should come along with your distributed parallel storage. Request time and latency is minimized really throughout the stack because a lot of times, as you saw in that diagram, essentially things are either node local or you're not having to, again, span or cross a network fabric multiple hops to get, say, from your storage media to a SAS fabric to a storage cluster node out through a network fabric to an iRODS server, back over the network fabric to a client. We want to really minimize that. And then another big thing is just if you're a large site with lots of petabytes of data, it's really attractive to be able to just keep a single copy and still have this type of resiliency. Usually this has been solved in iRODS classically by having multiple, again, copies, replicas of the data. Got a couple hundred terabytes, not a problem. That's cheaper than architecting around the problem. But if you have 100 petabytes, it's a different story. So fault tolerance. The resource servers, see all the available storage. We're introducing this concept here I'm going to use for the purpose of this talk of a physical resource server and a virtual resource server. And so the idea here is that the physical resource servers can impersonate virtual resource servers. That's what enabled that overloading in the previous slide when you're looking at resource 2 and 0 residing on the same VM. And another thing, to drive this for fault tolerance is we need to be able to monitor all of this and, automatically handle failures and do this failover correctly. So that all leads to only needing one, physical resource catalog and database running to keep things going. So again, this is distributed. The resource performance will scale with the backing storage. We really want those tightly coupled. One change we made versus years prior is we actually do think it's good if the iCAT is still hosted and co-resides on distributed parallel storage. Maybe it's in Crosspoint or SSD or a balance of both with caching. We really want it to scale independently of the resource performance. So in terms of parallel characteristics, one of the big changes from other designs we've done in the past is that the client can read and write to all resources at the same time. If you instead just kind of did the thing where you fake a single resource across your storage cluster, then with your load balancing, each client gets pointed into just one server and will only be able to they can see all the data, but they can only get reads and writes across those network interfaces for that particular node that they got chosen. This is why naming and creating virtual storage resources is really important, because basically all of the clients now can interact with all of the resources at the same time. This doesn't eliminate, but this kind of minimizes the data island lock-in that happens with iRODS, where you give a vault path on shared storage to iRODS and, again, exclusive access for that resource when it doesn't really have to be that way. This kind of mitigates it a bit. Clients, in the future science DMZ model, let's say, you have 100 gigabit clients and you only have 10 gigabit resource servers. Well, in this model, if you're pushing back and forth, a lot of data, say more than a file, you will be able to get higher bandwidth than you would have before. And so that's an advantage here. And really in the future, some of the multi-part support that's coming in iRODS really could provide true parallelism at the object level, and that's exciting. So this architecture is kind of getting ready for that. So again, to summarize here, we did not modify the iRODS code base to do this, and that's important that we stay with what the community is doing. It does let you be able to scale more horizontally when we're talking about parallel distributed storage and other scale-out shared storage backed by iRODS or backing iRODS. And none of this breaks compatibility to incorporate with other storage. So in terms of your composite resource trees can work as you'd expect. Like you could continue to add multiple versions of the reference architecture I showed you as members under that tree, as well as, say, then having object storage or other things that then you could do what we would call, a useful replicate, and you have useful replication. So you can merge this in with other tiered storage and storage virtualization approaches, just as you would normally expect. So again, how is this done? This work was originally done with 4.19. I've seen it work with 4.2, and we just are refactoring the automation and other things for 4.2.1. Similar to the talk Sanger gave, we think that having a dev test kind of environment that doesn't require actual hardware is good, so we kind of did the right thing there, I would think. And then, in this particular case, it was set up on a system running spectrum scale or GPFS as a cluster. So again, the high availability cluster monitoring and failover and everything was done with Pacemaker. If you're doing RHEL, we mainly target Red Hat builds like CentOS. CMAN would be for CentOS 6, CoreSync would be for 7. It's just what's kind of supported and tooled for that particular distribution and build. So we did customized resource checks for those. And so we had to do, think of this like hard links, that we needed to do link counts on the virtual resources. So we didn't inadvertently shut down an iRODS resource server daemon. We call that the physical resource server is the actual daemon. So actually when we're floating and failing over, we're not actually starting up and stopping iRODS resource daemons unless we have to, and that's less thrashing. It's designed for better efficiency and for microservice models in the future, which I'll get to. And so the impersonation happens just by overloading the host config. We haven't seen a downside to that yet. There may be some edge cases as we test more. And in this case, we use Galera cluster, as others have talked about and will talk about during this conference, for providing the high availability and multi-writer for the database. So this is going through one more time. This idea of these V, R0 through R7 are the virtual resources. These are floating IP addresses, essentially. They're not that fancy, really. And the PR is the physical resource. That's the iRODS resource daemon running. So the idea here is, again, you have you have connectivity to clients. They can all see underlying, iRODS objects stored in a vault. And the point is, as things fail, these virtual resources float over, and all the clients can still see all of the objects, right? So here's an example looking at a cluster, and we just zoomed in and used the resources for the resource servers in this example. So we're monitoring the physical resources with the iRODS OCF high availability plugin, or a monitoring plugin, and we have the IPs being monitored. The floating IPs are essentially the virtual iRODS resources. So here you see they have affinity where 7 maps to 7, 1 maps to 1. So they have a place they like to land, so it naturally rebalances itself as the cluster comes up. But here's an example. We, in the background, killed off everything to say, can you run with a single node? Notice we don't have quorum with a single node, but everything did start correctly. I wanted to do that as a movie, or do it live, but it was running back in the States, and I just thought it might be a little too hairy. So one more little note here about how the iCAT is scaled. So you have MySQL Galera doing state transfers at the very bottom. That's synchronization between the SQL instances. You can have really as many as you want. You just have to be aware that you're creating an extra copy of the data. The true multi-master, each master has a full copy of the data, and not a big deal at small scale, bigger deal at large scale. So that's why we chose 2 for the reference design for right now. So instead of doing HA proxy, we just did floating IPs, and so the failover looks like this. If there's an SQL failover, you'd just be floating that IP over. If there's an iCAT failure, you do the same thing. And it's really just to keep things simple, because there are a lot of moving pieces, and say you deployed this with Lustre backing it, it may already have Pacemaker and CoreSync running. So we really didn't want to have too many resource checks and too many different managers keeping track of monitoring and failure. So we were trying to keep everything as collapsed as possible. So I'm doing okay for time. I might go 1 minute over, but so we've been working with distributed databases for iRODS for quite a while. And so our experience is we didn't do a lot directly with Oracle RAC. Seen it work at other places, stood it up to test it myself. Just because of I think it works fine as a solution, and I think would be probably still in my mind technically the preferred solution right now. But there's the cost factor. MySQL cluster we tried. MySQL cluster did really bad for single client. It actually did really great in aggregate, and there were deadlocks everywhere. So the thing you have to realize about iRODS is it has really long running transactions, And those are the enemy of any distributed system, distributed databases especially, because long-running transactions just eventually time out and look like deadlock to most of these systems. So MySQL cluster, with some tweaking, we got really high insertion rates again in aggregate. And I think with more thread pool tweaking and even some of the code changes in the last couple of years, it could actually work pretty well. But again, there are just some deadlock issues there. PostgreSQL is interesting to me because it has a global transaction manager, and something is going to need to be the arbitrator with iRODS until these long transactions are cleaned up. So having that global transaction manager could be seen as a downside in other cases, but in the case of iRODS, it may help mitigate things. So we were able to stand that up. We did it quickly, just as a proof of concept. There's some more work to be done there. We got it working, but we were still seeing some problems with insertion interleaving among the nodes with auto increment that are usually pretty easy to tease out in these other systems, and it was just fighting us. So if you've solved that, let me know. Otherwise, we'll work on it some. MySQL Galera, again, works pretty well. The challenge we're seeing is we're still seeing a lot of deadlocks when you end up creating a lot of insertions into the same collection for multiple clients, and you're spanning multiple masters. Basically, the state transfers just can't occur correctly and in the right order due to the long-running transactions. So that's actually part of the reason back here why you do it the way that we do with just even doing DNS round robin on the top, is then there's no physical load balancer interfaces to constrain you as you scale. And we're able to float the DNS round robin, so if something fails, you're not going to get a dropout. But the other problem is we really want to actually, in this ideal model, be forcing a client to use a particular iCAT pass-through and a particular SQL, because we feel like the chances our clients are hopefully not working in different parts of the tree, and so they will kind of stay away from each other in terms of deadlock. If you had everything load balanced and just spread all the way through with Galera, that's basically like a worst case recipe to try to create deadlock between the masters. So last minute here, I'm only 1 or 2 minutes over. Getting on my soapbox here. Resource throughput and scalability, actually pretty good. We were able to get multiple gigabytes a second with small scale testing. We were able to get the iRODS resource servers in the past to keep up with the backing distributed parallel storage. There's still some optimization in there, be done there, but I specifically want to call out the TCP buffer work that was done for at distance enabling data transfer node type workflows with iRODS. That was really good work. That shows what's there. So I'm confident in this first bullet point. I'm not confident in the second one. I've been working with iRODS for 6 years, and this continues in my mind. Yes, I'm a systems type person, but it continues to be the biggest problem for performance and scalability. If we want iRODS to really manage end-to-end life cycles of research data, you need to be able to keep up with things. And it's only going to get worse. The whole industry is switching to NAND, right? Crosspoint is the new NAND, NAND is the new disk is the new tape, and tape is, you can pick what it is. The challenge is going to be, everyone is going to be IOPS driven in their engineering. And people that used to behave and create large streaming files are now going to create millions of small files again because they can. So even in the active archive side of things, this problem is going to come back and hit us really hard if it's not solved soon. So just wanted to highlight, that's the biggest thing on my mind. Atomicity of transactions, I think is still a problem, especially with those deadlocks and things I was talking about. You do not get deterministic behavior, let alone atomicity. So that's an issue. It's not only iROD's problem, but I would love to see more focus on trying to tighten that up. Multipart I want to call out as an awesome thing. It's really going to let us do interesting things with iRODS in the future. Good improvements for object storage, good improvements for true parallelism again at the object level. So want to see that work continue, want to find any way we can to help that. All the hacks that I kind of did earlier here with the whole virtual and physical resources, if you hate that, don't worry, it could be solved if we just could multipath resources. And that's doing that in the actual application layer is probably the right way to do that long term. And I'm going to skip over FastPath for now because I'm just going over a little bit. So future work, we're going to benchmark and test this more. We're going to look at PostgreSQL a little harder. Apache Trafodian It sits on top of HBase and Hadoop. Also interesting. I think CockroachDB, as Jason has been saying, is also very interesting. Desirable replication is more of just saying, exploring, okay, now we have this reference architecture, but now we actually want an archive or backup copy. How do we do that? We want to look at taking this architecture to more hyper-converged architectures, and I think even a lot of what we did here with the floating IPs and all this stuff could fit in really nicely to a microservice deployment model in Kubernetes, and as more people deploy HCI building blocks and move to this, that's going to be important too. So, thank you.
Questions right now? Yeah, hold on. Here it comes. All right, heads up.
Hi, thank you for an interesting talk. I had one question about the persona system. So why did you choose to go for persona and not just spawn a new VM?
Again, it's just minimizing thrash. When you introduce VMs and containers, there's just spin-up time involved. And here we're able to actually fail over very fast. Like as soon as that floating IP can move over to the physical resource it should be on, yeah, go ahead. As soon as that can happen, yeah, you're servicing requests again. So I think it was more just pairing it with kind of a Lustre model, if you're familiar with how Lustre does failover with pacemaker and core sync. But it could be done in a microservice model more as you described.
Sure.
Only went 5 minutes over.
So just a few observations. One related to MySQL, so the DB technology that you used. We tried to do some experiments with Galera. I think that the scalability of and the catalog performance depends too much on the DB, where you have to put metadata and you register every operation. So, I mean, it can scale for, for virtual resources, but doesn't scale for DB, in my opinion, because we tried for our test with 170,000 files, and we had bad performance to register all the metadata and the files, and so that's because you have to do 2-3 writes. And I think that something must be done on the DB side, or using another DB technology that you can scale, or you can use some other kind of distributed technology. And that's my first observation. Regarding the observation that the other guy did, you use pacemaker crossing, we used a lot this, but we think that microservice is better because you can recreate a container, what we do with the Rancher, but you can use Kubernetes. Mm-hmm. Recreating a container does take very few quick seconds, and you don't have to have all these technologies, pacemaker crossing, that it's something that is in contrast with microservice. You cannot use pacemaker crossing with microservice. It doesn't work, at least what is our experience. So I suggest to not use this kind of technology, but just you recreate a container, and then you have the service that is that comes again. So that's what we have done with Ranger. Availability is better with microservices.
Sure. So we'll see how this maps when we explore microservices as well. I would say this was done more for a static HPC deployment. People don't often yet, right, spin up Lustre, GPFS ephemerally. It can be done, but the idea here is to have kind of a static high-performance deployment. So it's a little bit of a different use case. But I would say until there is resource multipathing, still be having these virtual resources even in a microservice model is nice, because then you can collapse and expand the number of microservices, and like Kubernetes do that, but still be able to virtualize the resources and maintain a view of the full data. So the resource label becomes more of an affinity, to a particular microservice at a given time, but it gives you flexibility to scale and expand that you wouldn't have otherwise. But I'd be happy to talk with you after too. I was interested in your talk, and I like Rancher as well.
I suggest to people from iRODS to look at some technologies for the DB in order to scale it. I mean, also to use Raft, for example. because also setting up this kind of stuff requires a lot of effort. So you have to set up a MySQL Galera cluster. It's so easy for people to set up. So if you use, for example, Raft inside your iCAT, and then you use Raft congestion algorithm, and then you can set up easier for the DB. That's okay.
I agree. All right, so John is going to talk about the work that he's been doing at BioTeam to make all the